Reflection of light. Hello students, let us have a look at our 6th chapter, that is optics. After studying this chapter, you will be able to explain the reflection of light and image formation, define the spherical mirrors, discuss the mirror formula, understand the refraction of light, explain the optical fibers, define the refraction at spherical surfaces, understand the lenses, discuss the lens maker's formula, define the refraction and dispersion of light through a prism. Let us now understand what is reflection of light. We generally use mirrors to see ourselves in our homes. When we stand in front of the mirror, our image is formed because the light on us reaches the mirror and gets reflected from the surface of the mirror. The process of light returning from the surface of the mirror is called reflection. The surfaces which reflect light are called reflective surfaces. We can see images of objects placed in front of the mirror. Sometimes we can even see images on new steel vessels or ponds where water is still. So any smooth surface like steel or water can reflect light like any mirror acting as a reflecting surface. Let us imagine looking at a mirror. We have a floor down here as well. Let us suppose an object is standing on the floor. Now this is our eye seen from the side. The pupil there, some eyelashes. You are looking this way. So that is an eye seen from the side. Now whenever you look at anything, you are looking at a certain direction. And when you are looking at an image in mirror, you are looking in a certain direction. And light rays are coming from that direction into your eye. And the image appears to be in the direction in which the rays are coming from when they enter your eye. Let me draw the light rays reflecting off the top corners and the bottom corner. This is a solid object down here. Light is coming in, striking it, and light is scattering off from that object in all directions. Some of those light rays strike the mirror and enter your eye. And some light rays from the bottom corner also come and strike the mirror and enter your eye. So the point here is that when you look at the image in the mirror, you can see the image, but your line of sight goes in this direction. So if we take these two lines and extend them, we get a point down here. The object appears to be behind the mirror. Now when you get up in the morning and look at yourself in the mirror, you do not see the image of yourself on the front of the mirror like a painting. If you are 2 feet in front of the mirror, then your image is 2 feet behind the mirror. The point to understand here is that there aren't actually any light rays here converging to form an image. This is what we call a virtual image. No image really exists over here, but it appears as if the image is there. That is different from what we call a real image. A real image forms where light rays actually converge to form an image. An example would be a movie screen. If we have a movie screen here and a projector over here, projecting a movie onto the screen, then light rays are actually shining on the screen. You actually get an image here on the screen. Maybe some mountains or sky or something, but you actually get light rays landing on the screen. That is a real image. Spherical mirrors. Let us now see how light behaves with spherical mirrors. A spherical mirror is defined as a polished reflecting surface which is a part of a hollow glass sphere silvered on one side. Depending upon the nature of the reflecting surface, the spherical mirror is classified as concave mirror and convex mirror. Concave means curving inwards. A concave mirror is one in which the reflecting surface is formed from the interior surface of a sphere. Convex means curving outwards. A convex mirror is one in which the reflecting surface is formed from the exterior surface of a sphere. Radius of curvature is the radius of the sphere of which the mirror is a part. The letter R is used to represent the radius of curvature. Aperture is the part of the spherical mirror available for reflection. Pole is the midpoint of the aperture of the spherical mirror. The letter P is used to denote the pole of a mirror. Principal axis is the straight line passing through the pole and the center of curvature of a spherical mirror. Secondary axis is any other radical line passing through the center of curvature other than the principal axis. The normal at any point on the surface of a spherical mirror is a straight line joining that point to the center of curvature of the mirror. Normal at any point in a spherical mirror is equal to the radius of the sphere of which the mirror is a part. The normal at point A on the mirror is the line AC obtained by joining A to the center of curvature of the mirror. Principal focus, the rays of light parallel to the principal axis of a concave mirror after reflection pass through a point or converge at a point on the principal axis. This point is referred to as the principal focus or the focal point of the mirror. The letter F is used to denote the focus. The rays of light parallel to the principal axis of a convex mirror after reflection appear to diverge from a point on the principal axis. This point is referred to as the principal focus or the focal point of the mirror. Observe carefully the characteristics of the focus of concave and a convex mirror. In a convex mirror, the focus lies behind the mirror. In a concave mirror, the focus is in front of the mirror. Concave mirror is also known as a converging mirror as the parallel rays of light after getting reflected converge at the focus. A convex mirror is known as a diverging mirror as the parallel rays of light after reflection appear to come from a point on the principal axis. That is, the rays diverge after reflection. Focal length is the distance between the pole and the focus of the mirror. It is represented by the letter F in lowercase. New Cartesian sign convention for spherical mirrors. It is important to understand the sign convention used for measuring distances in the ray diagram of spherical mirrors. Observe carefully the illustration shown here. The principal axis can be compared to a number line. The pole of the reflecting surface is assumed to be the origin. All distances are measured from the pole of the mirror. The incident rays are drawn from left to right. The principal axis is taken along the x-axis. Distances measured along the direction of the incident ray towards the right are positive, and the distances measured against the direction of the incident ray towards the left are negative. Distances measured above and perpendicular to the principal axis are positive. Distances measured below and perpendicular to the principal axis are negative. Image formation by concave and convex mirror. Alright, now let us look at how images are formed by a concave mirror. What I am going to do is number these. This will be case 1, where an object is located there. Case 2 will be located on C, the center of curvature. Case 3 will be in between C and F. 4 will be on F, and 5 will be inside of F. So this is case 1. Here is my object. The first ray goes parallel to the principal axis, and then it is going to reflect out and then go through the focus F. So that is my ray. Here is C. Now the next ray goes through the focus. So it goes like this, and then it reflects out parallel to the principal axis. So what we get from this is the image. And I can say that for case 1, the image is located between C and F. It is inverted. As it is inverted, it is a real image and we would be actually able to project it on a piece of paper. And it is also smaller than the original object, so it would have a magnification that is less than 1. Now let us see case 2. Here is my object. See, the first ray goes parallel to the principal axis and then goes out through the focus F. Then the second ray goes in through to the focus and then out parallel to the principal axis. We get the image where these two rays converge. Now what we get in this case is that the image is the exact same size of the object. It is inverted, which makes it a real image. It is located at the same position as the object. So it is located at C, the center of curvature. Case 3. Here the object is placed in between C and F. Now let us see the ray diagram. First ray goes in parallel and out through the focus F. Then the second ray goes in through the focus F and out parallel to the principal axis. Now these two rays meet at this point. This is where we get the image of the object. This is larger than the object. It is outside of C. It is a real image, hence inverted. Case 4 is a situation where the object is located on the focus F. Now my ray diagram looks like this. The first ray goes through the focus F. It reflects out parallel to the principal axis. Now another ray through the focus is also going to behave in the same manner. The observation we see is that no matter what rays we get after reflection, they are all parallel and they will never cross one another. We do not get any image. Case 5 is where the object is placed in front of the focus F. Let us look at the ray diagram. The first ray will be parallel and then out through the focus F. Now the second ray passes through the focus and then out parallel to the principal axis. So this is how it looks. Now what we need to do is trace the rays back beyond the reflected rays. That will be behind the mirror. Now we find an image. The light rays are made to converge. They can never converge in front of the mirror. They converge behind the mirror. So that by definition is a virtual image. The image is upright, it is bigger and so has a magnification which is greater than 1. Now the last case is image formation with a convex mirror. The object is placed in front of the reflecting side of the mirror. Behind the mirror, we have the focus F and the center of curvature C. Now remember that the focal length will be negative. Let us now look at the ray diagram. Just like how we did with concave mirrors, the first ray will be parallel and then out through the focus F. Now the ray through F has to be traced back. The next ray goes in through the focus. Behind the mirror, the rays will be in dotted lines. Now these rays, after passing, reflect out parallel to the principal axis. Now to find the image, we have to go behind the reflected rays. So this is where we find the image behind the mirror. It is a virtual image, it is upright, and it is smaller than the object. So it will have a magnification between 0 and 1. Refraction of light. Okay, now let us look at refraction of light. You would have probably noticed that a spoon placed in water looks bent at the surface of water when viewed obliquely. The print on a page appears to be raised when the book is held behind a glass bottle filled with water. Now these are done by the tricks of light. Let us now find out how light rays travel from one medium to another. We will need a glass of water, milk, pencil, a torch aluminium foil, elastic band and a needle. We first have to prepare a point source of light. Observe how we do it. The aluminium foil is pricked by the needle and it is wrapped around the face of the torch with the elastic band. Now we get a point source of light. The water has to be given a cloudy effect. So we add a little milk to water, darken the room, shine the ray of light from the torch to the bottom of the glass. Observe the path of the ray of light. The path is not straight. This shows that a ray of light changes its direction of propagation as it travels from air to water. Now similarly, a pencil partially dipped in water appears bent to the observer. When a ray of light passes from air to water, its speed changes. Due to this, there is a change in direction of the light. This change of direction suffered by a ray of light as it passes obliquely from one optical medium to another optical medium with different optical densities is known as refraction. Now, whenever a ray of light is incident on a surface separating the two media, a small fraction of the light always gets reflected. Refraction can make an object appear to be in a different position. For the same reason, the part of the pencil which is submerged looks as if it has moved away from the part above water and it appears fatter. Now let us understand the phenomenon of refraction by studying the ray diagrams. Whenever a ray of light is traveling from a rarer medium to a denser medium, the refracted ray bends towards the normal. Here, IO is the incident ray, OR is the refracted ray, I is the angle of incidence and R is the angle of refraction. In this case, angle I is greater than angle R. If the ray of light is traveling from a denser medium to a rarer medium, the refracted ray bends away from the normal. In this case, angle I is smaller than angle R. The ray of light striking the surface of separation of the media through which it is traveling is known as the incident ray. The perpendicular drawn to the surface of separation at the point of incidence is called the normal. The angle which the incident ray makes with the normal at the point of incidence is called the angle of incidence. The angle which the refracted ray makes with the normal at the point of incidence is called the angle of refraction. The ray of light that has changed its direction at the surface of separation when traveling from one medium to another is called the refracted ray. The ability to refract light is called the refractive index. Refractive index of a medium is equal to the ratio of the speed of light in vacuum or air to the speed of light in that particular medium. Refractive index is equal to speed of light in vacuum by speed of light in the medium. This ratio is always a constant for a given pair of media. It is represented by a Greek letter mu. Dispersion of light passing through a prism. Now let us see how light gets dispersed when it passes through a prism. What happens when a beam of white light strikes a prism? When a narrow beam of ordinary white light is passed through a glass prism, different wavelengths travel through the glass at different frequencies and appear as a continuous broad band of different colors called the spectrum. This phenomenon by which a ray of light splits into its constituent colors when it is passed through a transparent medium is known as dispersion. Let us find out more facts about the spectrum. The range of visible light is 0.4 microns to 0.7 microns. Visible light has a large number of radiations having wavelengths ranging from 0.4 microns to 0.7 microns. That is, red light has a large wavelength compared to violet light. The component which derivates maximum is violet light, and the component which derivates minimum is red light. Now let us find out the cause of dispersion. The color of light depends upon its wavelength. Thus, red light has different wavelength compared to violet light. According to Cauchy's formula, the refractive index mu of a material depends upon wavelength lambda and is given by mu equal to a plus b by lambda square plus c by lambda to the power 4, where a, b and c are constants for a material. We know that for a small angled prism, deviation produced is delta equal to a into mu minus 1. Since wavelength of violet light is smaller than of red light, mu v greater than mu r. Therefore, on entering the prism, the violet light is refracted through a larger angle than the red light. Mu into delta v is greater than delta r. Thus, when white light enters the first phase of the prism, each color is refracted through different angle. That is, angle of refraction is maximum for red light and least for violet light. Mu equal to sin I by sin R. As a result, dispersion or splitting of white light takes place on the second surface of the prism and the colors are separated. Each color is deviated towards the box at the prism. The violet is deviated the most and the red the least. Lenses. Let us now talk about lenses. Most of us are familiar with lenses. There are two types of lenses, convex lens and concave lens. Convex or converging lens. An optical glass sphere can be cut in this manner to obtain a convex lens. There are three types of convex lenses, a concavo-convex, a double-convex and a plano-convex. Convex lenses are thicker at the center and become thinner at the edges. Rays of light passing through a convex lens converge to a point after refraction. This is the reason why a convex lens is also called a converging lens. Concave or diverging lens. An optical glass sphere can be cut in this manner to obtain a concave lens. There are three types of concave lenses, a convexo-concave, a double-concave and a plano-concave. Concave lenses are thinner at the center and thicker at the edges. Rays of light passing through a concave lens appear to diverge from a point. So, concave lenses are also called diverging lenses. Optical fibers. Okay, now we shall take a look at optical fibers. Optical fibers are long, thin strands of glass about the diameter of a human hair. They are arranged in bundles called optical cables and used to transmit light signals over long distances. A single optical fiber consists of three layers, namely core, cladding and buffer coating. Core is the thin glass center of the fiber through which the light travels. Cladding is the outer optical material surrounding the core that reflects the light back into the core. Buffer coating is the plastic coating that protects the fiber from moisture and from any kind of external damage. The bundles are protected by the cable's outer covering called a jacket. Now, how does an optical fiber transmit light? Transmission of light through an optical fiber is similar to the transmission of light through a hallway. When you have to illuminate a long straight hallway, you have to point the beam straight down the hallway. But to illuminate a hallway which is a winding one with multiple bends, you need to line the walls with mirrors and angle the beam so that it bounces from side to side all along the hallway. Now, this is exactly what happens in an optical fiber. Optical fibers make use of total internal reflection to confine light within the core of the fiber, has a higher refractive index than the cladding, and hence the light suffers total internal reflection. Although the cladding does not carry light, it is nevertheless an essential part of the fiber. The cladding keeps the value of the critical angle constant throughout the whole length of the fiber. Summary. So now we can conclude with what is optics. Optics refers to the study of light. The field of optics covers how light interacts with materials as well as the design and construction of instruments. Optics examines the behavior and properties of light over the whole spectrum, from ultraviolet to the infrared. Now, where do we use optics in our daily life? When we wake up and see the LCD of our alarm clock, we take pictures using the camera and also the cell phone. We control the television serials, air conditioner and a host of other things with the infrared rays of the remote control. Plasma LCD and LED television monitors, CD and DVD players and burners, barcode scanners, LASIK eye surgery, construction level alignment, traffic radar. These all are examples of optics in our daily life.